welcome you all. So we are doing a performance test on a 4-stroke petrol engine. So which include the performance has to be evaluated for a 4-stroke petrol engine. Along with that, we are doing a heat transfer, heat balance sheet for this particular experiment. So before we conduct any experiments, these are the observations that are to be observed, that has to be taken. Calorific value or lower heating value of the petrol is 45,000 kilojoules per kg. So this is on a general note, we will take it up. For every fuel, for every batch of the fuel, it will keep on varying, but somehow we have taken up a constant 45,000 kilojoules per kg for this particular calculation. Following this, we have a specific gravity of the petrol, which is 0.75. That's again a standard. Following this, we have a diameter of an orifice, which is 20 mm. Basically, where we are going to use a diameter of orifices, I'll let you know. So we have a cooling system. We have to measure the mass flow rate of the water. It's a water cooled engine. So we need to measure the mass flow rate of the water, which is a cooling water. So we need the orifice. We use the orifice and we use the manometer. The difference of the manometer will gives us an idea of the flow rate. Following that, I have a water flow rate, which we will keep it as 2 liters per minutes. We have to look into the orifice diameter, which is 20 mm. This is being used for to find the mass flow rate of air. Following this, we have a water flow rate. We call it as MW. We'll be using the same terminology even for our calculation, which we will set it for 2 liters per minute. Converting that, we'll get it as 2 kg per minute. Following this, we have a specific heat of water, Cp of water, which is 4.184. In general, we have taken it up as 4.19 kilojoules per kg degree Celsius, and we also have a manometer constant K as 2000 value. This is a typical tabular column that have been used for performance study, which has loading. We have a voltage and ampere, basically, that is current reading that has to be taken care. We are using electric dynamometer in this case for a petrol engine to load it. We also have time taken to consume 10 milliliters of fuel. So this is one of the column. As the loading increases, obviously the time taken will be much lesser to have 10 milliliters. So 10 milliliters has to be taken care. When we are while calculation, we'll take this 10 millimeter. That can be changed anytime. We can also keep it as a 20 milliliter or 50 milliliter as constant. But anyway, right now 10 milliliter will be the constant for us. Following this, the speed of an engine has to be tabulated. Following this, as I said the orifice diameter, we have it here. So we are using the manometer, between the orifice, we have H1 and H2. We also have delta H, that's basically the manometer reading in terms of meters of air, and or meters of water in this case, meters of water, and we call that as terminology as HW. That will be the same thing, we are using it in the calculation. The temperature has to be noted down for each loads. For each loads, there will be a different temperatures. So T1 is nothing but the inlet temperature of the exhaust gas. T2 is the outlet temperature of an exhaust gas. So what exactly an outlet and inlet temperature of an exhaust gas is? So exhaust gas is being cooled before it is let to the atmosphere. So the exhaust gas coming from the engine, it has to be cooled using the water. So whatever we are going to get before the cooling is nothing but T1, and whatever we are going to get after the cooling is nothing but T2. So T1 is inlet temperature of an exhaust gas cooler, and T2 is nothing but outlet temperature of exhaust gas cooler. So obviously we can expect a T1 will be greater than T2. Regarding T3 and T4, it's a cooling water coolant temperature before and after respectively.
Single cylinder 4-stroke diesel engine performance test. Okay, engine Greaves engine company engine. Okay, single cylinder cooling system ಬಂದ್ಬಿಟ್ಟು air cooled engine.
Air cooled. It's a air cooled engine. We have it's been connected to electric
engine crankshaft front pulley, rear ಅಲ್ಲಿ ಒಂದು pulley ಹಾಕ್ಬಿಟ್ಟು pulley to drive electrical generator. Okay, 75 mm dia rear pulley, generator pulley 150 mm. Okay, next generator power produce voltage.
We have an electrical loading system that can be controlled from the control panel, which is being shown now. So we have a display for taking up the reading of speed of an engine. Right now it is showing as 0 since it's in a stationary condition. We have voltage reading, we have a current reading in terms of amps, that's amps reading now. Following this we have a temperature reading, we have T1, T2, T3, T4. We have a single display, but using the knob we can change it to any temperature. Since you can see the knob, it's a selector switch. We have 4 different temperature what we have already studied about. So T1, T2, T3, T4. Following this we have a fuel burette where we are going to use this for taking up 10 ml of reading, 10 time taken for 10 ml of fuel consumption. To switch regularly, the fuel will be taken from the tank. When we are taking up the study, we have to switch on the knob where the fuel will be taken from the burette only for that particular time. Following this we have a manometer. H1 and H2 are the reading we are going to take up. So that's about the manometer. Following this we have a rotometer where we are going to take up the mass flow rate of water for the cooling purpose. So it's a fixed one, 2 liters per minute is what we are using it for. So this is the exhaust calorimeter, and we have a temperature T1 sensor, that's an inlet temperature directly from the engine. The exhaust gas will directly hit into the calorimeter, that's the T1 sensor, and we have the T2 sensor just downstream of the calorimeter, so that's T2. Following this we have a coolant inlet temperature, outlet temperature, coolant outlet temperature T3, and that's the sensor for that particular this one. Following this inlet water temperature is T4. We have, so this is the calorimeter. We have an exhaust gas inlet for the calorimeter, and that's the T1 temperature sensor, that's the T1 before the calorimeter. Following that we have another temperature sensor after the calorimeter, so that is temperature T2. So we have T3 water outlet temperature T3, inlet temperature, water inlet temperature T3, and water outlet temperature T4, which is being used for cooling purpose. So this is an electric loading system. we have an switch on and switch off switch, I mean basically the switch for switching on and off of the loading. Once we are switched on, there are 6 or 5 stages of loading, and I mean this is where the loading takes place. Loading of at 5 different stages. Along with this, mechanically we need to load. This is an electrical loading system. We have we also have an mechanical loading system attached with the electrical loading. So along with the electrical loading, we also have a mechanical loading to balance it. And also this is going to be easier for the calculation rather than going with an electrical loading. So we have torque arm that is being connected to a spring balance at the other end of the arm, and one end of the arm is connected to the shaft that is connected to the electric generator. So once we load with the electrical once we load to the electrical generator, the generator will slightly swivel to the right, and we need to adjust the reference point by loading mechanically using the spring balance. And once we load it, we'll get the mechanical reading. We will get the mechanical reading on the scale. That's the reading of the mechanical spring load. So once we load the electric generator, it will swivel to the right. This is what you can see, and you can see the pointer. That's a reference point. Once it swivel, it won't be in its reference point. So by loading mechanically using the spring weight, spring load, we will make it to a reference point so that 2 needles will focus each other. So that reference has to be maintained, and this process has to be done for each loading of the electric generator. Each time we have to follow the same procedure for each of the electric generator loading. Now we are starting the engine. This is a rope start method. So we need to crank using the rope. This is how we do the rope crank. Completed the experiments. Regarding the calculations, we have a calculation P2 brake power. 2 pi n is already, we know that it's the speed, we have it in the tabular column. We have W, which is a loading, into 0.2, that's the torque arm radius. We have a ratio of pulleys, which is going to be a 0.5, that is basically 75 mm by 150 mm, which we are well known. So by substituting the value for each cases, for each trials, for each loads, we will get the BP of that particular load. Brake power, brake horsepower, it's also called as brake horsepower. Following that, we have a mass of fuel consumption. We have a specific gravity of a petrol, which we well known during our observation. We have into 10. 10, as I already said you, that's basically 10 ml of fuel consumption. That's the time we have taken up. That's the T, time consumed for, time taken for consumption of 10 ml, and conversion of 1000 will all get us in terms of kg per second. Following that, specific fuel consumption. We have mass of fuel consumed to 360 by BP will get us the value of in terms of kg per kilowatt hour. Following this, we also get brake thermal efficiency, BP into 100 divided by mf into CV. mf is nothing but mass of fuel, and CV is calorific value of the particular fuel, which we have taken up in observation. That will be in terms of percentage. Getting back to the amount of air consumed or volume of air consumed, we have 0.64, that's basically a CD of an orifice meter. 0.64 pi d square, d is nothing but diameter of the orifice. We have 2 g into basically h in terms of air. They are expecting in terms of air to get it for particular this formula. How do we get head of air? Because we measured it in terms of water, so to convert that we have a formula in terms of head in terms of air. So we already know HW, H1, H2 we have already taken up from the manometer, and difference in H gets us HW. So by using the row of water and row of air, we will get it H in terms of meters of air. Here it was in terms of water. Okay. So from that we can calculate the VA, volume of air, in terms of meter cube per second. Following this, air fuel ratio has to be calculated. We know already the row of air, row of air, volume of air we have calculated. We have mass of fuel that will get in terms of, it doesn't have any percentage since it's a air fuel ratio. Following this, we also have a volumetric efficiency. 60 into VA is very well known to us already. We have pi by 4 d square L into n by 2. D, capital D, it's not a small d. Small d represents the orifice diameter. Capital D represents bore dia of the engine. Following that, L stands for stroke length. N is nothing but again the speed. So all put together, we should get in terms of percentage volumetric efficiency. This is all about the performance. Following this, we also have a heat balance sheet. So heat balance sheet is nothing but wherever the heat is being inputted and how it exactly dissipated. So we have heat input as mass of fuel. Heat is being inputted through only burning the fuel. So the amount of fuel it's being burned and calorific value. So it will be in terms of kilojoules per minute. Kilojoules per minute. That's the heat input. That's the only way we input the heat. Following that, we have a heat output. So heat is being dissipated by converting that into a brake power. So heat equivalent to brake power. We also have water carried by cooling system. So that's basically the cold water takes away some of the heat, and exhaust gas carries some of the heat, and there are some unaccountable losses that cannot be calculated. So all put together we have Q out, heat out. So heat equivalent to brake power is nothing but brake power we already calculated in terms of kilojoules per second or kilowatts. To convert it into kilojoules per minute we use into 60. So we use the multiplication 60. Following that, heat equivalent to the water that is being taken away, mass of water, Cp of water, T4 minus T3, that's the difference of water, hot water and cold water. So that should get in terms of kilojoules per minute. Following that, we have a heat carried by exhaust gas. How can we calculate the heat exhaust? Basically, it's mass of gas to Cp of this particular gas. We take it as air, Cp of air, and T1 minus T2. So Cp of air is very well known to us, whereas mass of gas is to be calculated. Mass of gas is nothing but mass of air plus mass of fuel is nothing but the mass of gas. Mass of air can be calculated by using rho pi d square L into N by 8. So this will be in terms of kg per minute, and from that we can calculate mg. Following this unaccounted losses, it's nothing but Q in. Obviously it's a energy conservation theory. Energy neither be created nor be destroyed. Q in has to be equivalent to Q out, and out of that Q in minus all of this together should be the unaccounted heat losses. So use your manual. So there is an way how to represent the heat balance sheet. I have just shown you the heat balance sheet calculation. That has to be heat has to be in terms of heat balance sheet itself. Please refer your manual for heat balance sheet format. Okay, so you have to represent all these calculations in terms of heat balance sheet itself. Okay, finally the graph we need to plot 3 different graphs. So it's brake thermal efficiency versus brake power, brake horsepower, volumetric efficiency versus brake horsepower, and SFC versus brake horsepower. So this gives the performance study of an 4-stroke petrol